My presentation today will sort of come in two parts. The first is a sort of an update as to where we are in the wet areas mapping program, and then pose some questions after that. And really the issue though of riparian management has been something that I've been quite keen about for the last most of my professional career. And really much of my interest is somehow linking riparian management to the landscape level and linking tactical with strategic planning. So a lot of has been changing with my employer downtown, and our, you know by now that our department has merged with Alberta Environment, and this is one of the things that's really guiding what's going on in our department. And essentially, as the world is watching us to provide environmental leadership, and this is really driving a lot of our decisions downtown right now. And one of the messages that we keep hearing from our executive, and we're feeding them as well, is we really need to push the envelope in terms of creativity, innovation, risk-taking, and really rethink environmental stewardship and monitoring. And some of the key points here are really driving even how we're structuring our new department and creating some of our spin-off agencies. So one of the keys to forest management in the future is going to be the acquisition of LiDAR. And this gives you a little bit of an update as to the LiDAR status as it is today. So we currently have about 28 million hectares. Part of that is in the white zone. But the primary driver for the acquisition for the government of Alberta has been our department, and actually specifically Forestry Division. And we are in a process right now of trying to acquire data for the areas in the north. And I'm hoping by next week we will have this strip here filled in. And year by year we hope that we'll have complete coverage of Alberta's green zone. It's a huge investment for us. Over $20 million just for the green zone ourselves. It's considered to be medium quality data, but we know there are issues with it. And but because of the size of this investment, we really want to see this used throughout the innovation profile in Alberta. So John mentioned this slide this morning, but why do we seek excellence in information? And it really boils down to these four cogs. One of them is we want to become more efficient as ourselves as an organization. We want to be able to streamline our approvals. We want to be able to target our auditing in the field and our monitoring. We want to inform our plans. We want to make sure that we have the most effective policies. We're also very cognizant of the fact that we have to make sure that we have an industry that's very competitive. We want to reduce planning and operational costs. And of course, we want to enhance stewardship throughout the province. I've added this last cog in the presentations I've given over the last 6 or so months. And really, we want to see better information moving into the innovation system, even here within the University of Alberta. The wet areas mapping, I know there's some people in the audience here today that haven't seen this before. My apologies to those that have. But this is essentially what the model is doing. It's looking at the topography, and we're mapping where stream channels are. Most of these are hidden. But the real innovation is deciding where the surface water table is between two different stream channels. And in this particular case, we're simply mapping it in color coding. So the darkest blue here is where the water table is in the top 10 centimeters. You would have a glycolic soil, probably organic, maybe organic. Machinery would have a lot of soil disturbance. And as we're moving away, we're changing the color code here from 0 to 10, 10 to 20, 10 to 25, 25 to 50, 50 to a meter. And this cut section here is portrayed down in the bottom. So the black line is the surface of the earth, here at 1 meter resolution. And the model is determining where it thinks the water table is relative to that surface. So there's a slope here. The model is predicting the water table is down quite a depth. We don't actually calibrate this, but we know this would be a very dry habitat. The water table is then coming to the surface in this wetland complex. There's actually a little tiny bump right here, which corresponds with this dry area. It darts around, comes back up to the surface at 3 different points here, and probably small ephemerals. But having this type of information is very valuable because you can start developing some functional relationships as well as operational designs. The one thing that we wanted to stress, though, is that the four features showed colors on a map, and that's one of the desired things that we want. But we also have to remind ourselves that there's an immense amount of data that's behind the calculation of that, and that data is available to any researcher that wants it, as well as to the forest industry. So the model that we use is determining these depths of water on a 1 meter basis, using principally the topography. And so every square meter of that landscape has a flow direction raster, so we know which pixel moves into the next and the next and the next. We know how many pixels are flowing in, or we predict how many pixels are flowing in to a given point, and then that helps to generate the depth to water raster. These rasters are all available at 1 meter resolution, and then people can alter them as they see fit. But all this data now is at the University of Alberta and supports 5 graduate students now that are taking this type of information and making or attempting to investigate whether there's functional relationships with anything from plant performance all the way to wildlife habitat. This is, we've seen a few slides like this, but and John showed it, but this is north of Peace River. This is our hydrology layer turned on, and we can see here that there's not a lot of water information that we have up front in the planning process. But we see a number of buffers here, riparian zones. And so what that necessitated was that somebody would go out and walk many of these to confirm that they're there, to confirm that others are not wide enough to be buffers. They might be equipment-free zones, very labor-intensive. But also the absence of knowing this when a forest management plan was developed was you've missed the opportunity to develop or to incorporate a lot of these strategies into your management planning up front. This is the bare earth, and then this is the wet areas mapping determined. And you can see here that our little modeling guru 4,000 kilometers away has put his stream channels where we saw the buffers in each of these cases. So the real question that we have is, if we have this better source of information up front in the planning process, can we better account for water on the landscape? Can we better protect it? Which is one of the goals that we would have from riparian management itself, which was developed in the absence of having this type of information. This just sort of reiterates what we're seeing in the field. This dark blue is where we have a water table is close to the surface for most of the year. And as we're moving away, we're seeing that the drop in the water table, the change in soil properties and operations. Incidentally, it's usually around this interface where you see the really big pumpkins. Wet areas mapping is one of our largest research projects right now within our department. It spans about 20 million hectares, and the data has been released and shared across the entire government of Alberta, so there's about 4 departments now that use this information. The newest thing, though, is that, and I'll show some results, is we think we were good in this particular area. I'll back up a little bit. This is in the green is what's completed to date and has gone public. It's about 14.2 million hectares, and the public announcement for the data availability of that went out 2 or 3 weeks ago. And 14.2 million hectares is 426 billion pixels of information. And we have funding in place for the next 3-year period to map much of what you see here. And again, the data has gone out, consistent with the new theme of open government. We're hoping that we're going to have a second data release for the DMI East FMA and portions of the Alpac FMA by May of this year. So over the last, we've been mapping since 2008. The research itself started in 2005. And in the lower foothills, we think that we were fairly decent at finding out where we had hidden stream channels. The one area that we were a little bit more disappointed in was picking up the more obvious wet spots, and that was some of the wetland features. And we heard before in the last presentation that the LiDAR is not always, or does not always give you the information that you think you have. And one of the things that we found is that we have to operate at the very high 1 meter resolution to keep the integrity of stream channels. But we also bring in a lot of artifacts. And what we found in particular was, as we moved in to work around wetland complexes, the DEM was false. Often the DEM that was produced would be falsely elevated because of hits off the top of dense vegetation, and the real culprit was thick peat. And so in areas of the foothills, we would often, this might be a wetland complex, parts of it would come out as dry, parts would come out as wet, and that caused, you know, it was frustrating because it's the most easy thing to see when you're in the field, but it would be missed at times. So in 2010, we slowed down our mapping and started to focus our graduate students on coming up with a better approach to map wetlands. And we started to mine the LiDAR data, looking for patterns and a number of other factors. And we did an extensive amount of field work. There's about 400 plots in the LPAC FMA. And we've come up with a new modeling process, so we've started mapping again. And this is one of the demonstrations. So these are wetland complexes. And so this is the new modeled output. And this is how we're moving for the northern half of the province. And if I can go backwards, so you can pick out any one of these wetland pockets, and the new process picks up most of the boundaries very, very accurately. And in fact, now what we're doing is we're trying to create a separate data layer for the wetland feature out of the LiDAR and have that as a separate deliverable. What's incorporated in this is a wetland feature, and then it feeds into the wet areas mapping process to create one data layer. But in the future, we'll have a distinctive layer that's probably going to inform, or we hope, the wetland process. We want to go one step further. This is the Emond experiment in northwestern Alberta, and what we're doing was mapping out, field validating the bog features on the landscape. We wanted to go one step further though. We wanted to see if we could use this approach to help understand better the connectivity across these peat lines. And these are the field validated flows. One of them we got wrong. The yellow ones are hard to see in this room probably. They're ephemeral draws, probably only connected in certain years of really, really high precipitation. And the green ones where we had flowing water in the air. This type of information of the connectivity is of immense value to us, mainly in connection to spill mitigation for the energy sector. Now, shifting gears a little bit, the question then comes up is can we use this information to better inform or protect water on the landscape? And we have to remember that the old policy was developed when we didn't have these types of data sets. And the absence of that type of functional data set was a very strict policy. And so now we operate in an environment where we have much better water information that can be used up front in the planning process. But also, one of the questions that we asked ourselves was, can the depth of water partially inform riparian width? And we throw out an example here where we have a riparian zone that was very, very narrow, very probably had steep banks on the edge, versus one where we have more of a floodplain extending out. And of course, correspondingly, could that inform what our buffers might be? The other issue, though, that we were very interested in is this issue of where do we need a buffer and where do we not, and where do we start it on the landscape. And the existing requirement is stream width, and we know that's very problematic in the field, but again, it's a tactical level. And so one of the questions we're asking ourselves is, can we move away from using a field measurement to something that's more functional but also can be identified up front in the planning process? And the one that we've asked ourselves is can we go back and use some of the raw data, being the flow accumulation, to define where a buffer starts? We don't have an answer for that yet, and I'll show you why, and also to classify our stream channels. So for instance, on a landscape, instead of saying I start a buffer in a 40 centimeter stream width, could I say it should be a point on that landscape where the flow accumulation might be 25 hectares? And if you could come up with that magic number, then you can incorporate it up front into your planning process. One of the challenges that we've run into in doing that approach, and we don't have an answer today, has to do with how we do our modeling, because the modeling was never designed to answer that specific question. But this is a 50 by 50 kilometer polygon that we do the wet areas mapping, and actually it extends a couple of kilometers, and there's always this overlap between these tiles to make sure that the wet areas and stream channels are merged properly. The problem that we've run into right now is that at the edge of this tile, we set the flow accumulation, or the model sets it to 0. So we think that within the tile itself, we can do stream classification work and work with respect to flow accumulation and buffers. The challenge and problem that we're going to have is how we do that at the edge, where it's artificially a 0 value. We don't know the answer to that question yet. We're working with folks down or my team is working with folks down with Esri, but we don't have an answer to it. And of course, that's how everything is seen together. The other issue that we have, or question that we have is, and we've heard a little bit about it this morning, is how can we start integrating a lot of these LiDAR data sets together and other functional data sets to inform as to whether or not there's areas along the riparian zone that have higher biodiversity importance than others, and can that inform into a decision framework. One of the areas that we're very much interested right now in the department is trying to merge all these data sets together. So we've got LiDAR data that we can infer certain pieces of information. We can look at whether it's a simple overstory or a complex stand structure. But also for many of these areas, we have existing studies throughout the province on caribou habitat, vegetation mapping, wet areas mapping, fisheries, etc. One of the things we're starting to ask ourselves is, can we start merging some of these data sets together in a new project to try and come up with better landscape level mapping information that can then better inform the planning process. Just in conclusion, these are our graduate students. The wet areas mapping program over the last 2 years has really taken off. We now fund about 5 graduate students here at the University of Alberta. These are the total list of people that were engaged today. David Kemplis has graduated. These were our bog mappers last year. And we continue to enjoy the support of quite a few different organizations. Really the message here today, though, is we want the innovation to continue with respect to a variety of questions, including riparian management. But we also want to see data sets like the LiDAR come in and inform some of these so that we can shift to alternative policies and ideally move to the forest level planning. Thanks very much.